Hello, everyone. Welcome to my virtual talk at ICASSP 2023. My name is Homa Esfahanizadeh, and I'm excited to present our recent work, Task-Based Neural Data Shaping via Mutual Information. In this work, we developed InfoShape, a solution that enables data owners to share their data for a specific purpose while preserving their privacy. This is a joint work with Bill Wu, Mania Gobadi, Regina Berzili, and Muriel Medard. Machine learning algorithms have attracted significant attention for many classification tasks. However, access to publicly available data is often limited, making it challenging to develop competitive models. Imagine several data owners, such as hospitals, who want to send their data to the cloud for a specific ML training task. But we also have the threat of adversaries who misuse data for other undesired purposes. Some federal regulations, such as HIPAA, actually prevent hospitals from sharing raw information of patients. To address this challenge, our goal is to give data owners greater control over the content they publicly share. Our approach involves designing a task-specific lossy encoder, and for this, we leverage the notion of mutual information, which is a measure of dependence between two random variables. For designing the task-specific lossy encoder, we have two goals. Privacy goal and utility goal. As for privacy, we want to minimize the mutual information between encoded sample T of X and sensitive label S of X to remove as much private content as possible. As for the utility goal, we want to maximize the mutual information between encoded sample T of X and the public label L of X to preserve as much necessary content as possible. Here I show you how we train our task-specific lossy encoder that we call InfoShape. We modeled the encoder with a neural network whose weights are adjusted to maximize the mutual information between T of X and L of X and minimize mutual information between T of X and S of X through a Lagrangian optimization. These mutual informations are estimated and combined with negative sign to form a loss function to improve the performance of the encoder. Once trained, the task-specific encoder or InfoShape can be used at each data owner's side independently to shape their data before publishing. As I mentioned, mutual information quantifies how much information on average can be obtained about one random variable by observing another random variable. For estimating mutual information, we use the Donsker-Varden representation of MI, which states that the mutual information between two random variables, alpha and beta, can be obtained by finding a function f that takes two inputs and maximizes this expression. In this expression, the first expectation is taken over the joint probability of alpha and beta, and the second expectation is performed over the product of the marginal distributions of these two random variables. For having better numerical stability when we do the numerical optimization, we also have an additional regularization term. We have this optimization problem. We model the rich set of functions f with a neural network that can take different values for its weights. We also replace the expectations by a statistical average over public data sets, and we will then numerically perform this optimization using the stochastic gradient descent algorithm. Therefore, we train the task-specific encoder iteratively using SGD, and at each epoch, we iteratively estimate the mutual information and use them to obtain a measure of the performance of the encoder to improve it. And next, I'll present some interesting simulation results. Our dataset is a synthetic dataset with 10,000 samples, each of size 10 and associated with a public label and a private label. The left figure here shows a three-dimensional representation of the samples colored based on their public label, and the right figure shows a similar representation, but the samples are colored based on their private label. These two figures show the estimation of mutual information at different epochs of training the encoder. The top figure shows the mutual information between encoded sample and public label, and the bottom shows the mutual information between encoded sample and private label. Let's take a look at the top figure first. When at the first epoch, when no training has been done yet, the mutual information is about 0.06, which goes up at higher epochs as intended because it is a measure of the necessary content. An upper bound is the mutual information between original sample and its public label, which is 0.48 in this example. Now let's take a look at the bottom figure, which is the mutual information between encoded sample and its sensitive label. At the first epoch, it is 0.19, and at higher epochs, this value goes down as intended because it is a measure of privacy leakage. Again, we have for comparison the upper bound, which is the mutual information between original sample and its sensitive label. These two figures show the predictive utility of two classifiers that are trained on encoded data for predicting the public label on the left and private label on the right. Let's take a look at these results. The red curves show the performance when the classifiers are trained on randomly encoded data, and the green curves show the performance when classifiers are trained on noisy data. Now we will show the performance when classifiers are trained on our InfoShape encoded data. As for public label, it shows a higher predictive utility compared to the baselines, and as for private label, it shows a dramatically lower predictive utility as intended. For comparison, we also printed here the performance when training classifiers on original data. These figures show that an adversary who has access to some related public data and also the InfoShape encoder cannot infer sensitive information from InfoShape encoded data of other organizations. As a summary, we presented InfoShape, a task-specific, lightweight, lossy encoder that allows data owners to share their data for a specific task while it is less helpful for other sensitive tasks. Our codes are publicly available, and please let us know if you have any questions, either by email or during the conference. Thank you very much for your attention.